Let me do one more thing, I guess. Yeah. Okay. Hello, guys. Thanks for joining. Today, I'll talk about time period of a pendulum. And so let me say, so this time period of a pendulum. And in particular, if I can get the time, I will talk about how exactly it changes with amplitude. So what is a pendulum to begin with? So we just take any string and you hang a mass on it. It doesn't really have to be spherical. You take any, preferably a light string, but when we say light, we always clarify light with respect to what. Like when we say the mass of the string is small, you should clarify with respect to what. The mass of the string should be less compared to the mass of the bulb here. So this has a mass m, and string also will have the mass. So mass of the string, if I just use the letter S, should be less than mass of the bulb, let's say. And then you would say how much less? If you say this is about one times less than, so let's say this is one, let's say ms over the bulb is less than 1. If it is about 0.1, that means you will make an error of 10%. If this is 0.01, and you will make an error of about 1%, and so on. So as you make this smaller and smaller, your accuracy in the experiment gets better and better. So that's the kind of stuff I want to talk today. How good is the expression of a time period, and what are the errors associated with it, especially with respect to the amplitude. So that's a pendulum. You hang this from a ceiling or any rigid or a fixed point, and this is of length L, let us say. So this is of length L, and you pull this to the right. So it's the same mass, and that is pretty much described by this angle. How much you can pull this to the right, we will give this by an amplitude phi naught. So this will be amplitude. So that means the initial angle. This should be differentiated from phi, that's the angle itself. Right? So that means to say when it is somewhere here, once you leave this, that's angle phi. So any other angle other than the initial angle, which will always be less than that initial angle. So phi is always less than phi naught. Right? So that's what we would like to talk about. Now it was realized, apparently, I exactly did not know the history of this. It was realized that the time it takes to go all the way to the left and come back, t, that's called the time period. So this will call the time period. The time period t is pretty much related to the length and a constant g, which turns out to be the acceleration due to gravity, and it is the square root of that comes in. So there's a factor of 2 pi that's there. This is a pretty remarkable result. This was realized, I think it's associated with Galileo all the time. In 1600s, and it is the note that it is independent of mass. So there is no mass in here. and there is no amplitude. The independence of this time period with respect to mass was very surprising in those days, because remember that Galileo in 1600s came before Newton, and in those days it was common to expect that if you drop two objects, a heavier object would move or will fall faster. It was not realized until Newton's time that if you were to remove air and drop two objects, heavier object and a lighter object falls at the same rate. And that is a non-trivial result, in the sense that that implies what we these days interpret it as an inertial mass being the same as the gravitational mass. If just to take away the triviality or the non-triviality out of that, think of it in a charge context. If we are doing electricity, then things a positive charge and a negative charge, or let's say a proton and an electron, does depend on the mass. So it being independent of mass is a very non-trivial result, but nevertheless that's known, and often in our introductory level physics, once you make the demonstration, it's considered very standard. So it is the time period. That means again we have a mass hanging from a string of length L, and you measure the time it takes to go all the way to the left and come back. And if you were to do that, this can be easily done in the sense, hang that, and instead of doing for one oscillation, do that for about 10 or 20 oscillations, take the time period, divide it by the number of oscillations. It comes out reasonably good measurement. And if your measurement, you are a little careful with that measurement, it's very easy to get about 1%. Let's say 5% accuracy, because of the amplitude. I'll talk about the amplitude very quickly. It's very easy to get about 5 or between 1 to 5% accuracy. When I say 1 to 5% accuracy, it means 2 significant digits. If you're measuring in seconds, we are talking about, it is easy to get the second digit. Like let's say the time period came out to be about 2.1 seconds. So you made a measurement for 20 oscillations divided by 20, and you got it at around 2.1 seconds. And then you put this length of the pendulum in this expression and got the same similar number. These two numbers will, it might be easy to compare the second significant digit very easily. That's what I mean by it is, it's a very good expression. And but then we still have this, we would like to understand why does not it depend on the mass, and why does not it depend on the amplitude. And today I'll talk about, does it depend on the amplitude or not? If you were to extend this very far, how much is the error you make? And I would like to talk about that amplitude dependence. The mass dependence, to our knowledge as of today, we really think that this time period is completely independent of this mass when it is falling under gravity, in the sense that it's a gravitational. So Earth is under here, right? So this is Earth. It's not flat, so this is a spherical Earth, but when you're really close to the surface of Earth, the acceleration due to gravity G is pretty much constant. And this is to 2 sig digits, this is exactly 9.8 meters per second square, pretty much everywhere on Earth. Unless you go to the third significant digit, it does not change at all. So we will not investigate the mass variation. It turns out, to our understanding, it is mass independent, but let's talk about how does it change with respect to amplitude. So for this purpose, we will use the idea of conservation of energy. One can start with either Newton's laws, which is interpreted in terms of force or in terms of energy. So let's think in terms of energy. Again, this is the pendulum, and that's your vertical, that's the length L, and that's your mass M. When it falls down here, when it is really at the extreme bottom of that trajectory, it has fallen down a little. So that's the length it would have fallen down. That's the height. And that much of height is associated with a gravitational potential energy. So energy in this context comes in two kinds. So there is kinetic energy. So that's, we will associate the letter K with it, and we will say this is half times mass times the velocity of the bob. So how fast is it moving? So this is the energy associated with motion. If you're moving with respect to an observer, then you have a kinetic energy. There's also a potential, or let's say gravitational energy. It's called gravitational potential energy. That's you, let's say U of G, but here there is going to be only one form of potential energy, so there is no necessity for the subscript G. So that's equal to M times G, where G is again the acceleration due to gravity, and the height h. And then the question comes, height h with respect to what? Whenever we say height h, there has to be a reference. So let's choose our reference to be down here. So at this point, h is equal to 0, and that's your height h. So the small amount of height it gains when you pull the pendulum to the right, that's your h, and when it is right at the bottom, that's equal to 0. And the idea is that based on Newton's second law, it is true that the sum of these two quantities, the amount of energy associated with motion and amount of energy associated with height, it's only the vertical height, it doesn't matter when you're going horizontally, you can move as much as you want, and there is no associated gravitational energy to that. So these two, the sum of these two has to be the same. That's the idea of conservation of energy. When you drop it, so when you start from here, there is no velocity. So you, let's say you just start from initial velocity equal to 0. So in that case, there is a lot of energy associated with height, but no energy associated with velocity. And right at the bottom, there is no energy associated with height, but there is a lot of energy associated with motion. And in between, there is somewhere there is a distribution between the two. So these two has to be equal to same. So K plus U has to be equal to a constant. If it's a constant, then what that means that I can associate this constant to the extreme right, and that's what we would do. One more feature, since things are moving in this direction, so the velocity is this one, right? So it depends on, velocity is distance over time typically, but if you're going on a circle, so let me quickly say this. So this is a circle, and remember this is part of a circle, right? So if you keep going around, so this is the center of the circle. So the pendulum is pretty much, the bob of the pendulum is pretty much going along a circle. So if you have an arc formed here, and that's your angle phi, that's your L, and the distance S on here, so this is the arc length. So remember your geometry, the arc length of a circle is radius. So S is equal to L times phi. Typically, you would say it is a radius times the angle that you subtend. Angle, if the way to remember this is that if this angle was 2 pi, which is the total angle, 2 pi, when you measure it in radians, the total angle is 2 pi, otherwise it is 360 degrees. Remember, 2 pi radians is equal to 360 degrees. So if with that relation, if you were to say what is velocity, velocity will be the distance traveled over time. So that's s over t, let's say. You have to say change in s over t, but let me just say it is s over t, and this will be L times phi over t. Let me say this is change in s, change in time. That's your change in angle times change in time. So basically what we are saying is that velocity, instead of being the change in distance over time, if you take out the radius, it is basically the change in angle over time. So velocity is radius, which is length L in this case, times the change in angle over time. With that idea, K turns out to be equal to half m L square, because there is two velocities, so L square. And this whole quantity, we will say, is instead of change d phi, so let me write this as d phi over dt. So this is the change in phi. This represents change in phi, this represents change in t, and then you say that's square. What is the height h here? So similarly, what is the amount you have dropped down here? So that's your height h. H comes out to be equal to, the total height is the length L itself, and you have to subtract out this quantity using the right triangle. We have this to be L cosine phi, right? So this is L minus L cosine phi. So the potential energy that we are discussing here, that comes out to be mgl minus mgl cosine of phi. So what's the total energy? That's equal to half m L square d phi by dt. The change in angle with respect to change in time, mass and length square, plus mgl minus mgl cosine of the angle. So at any point, this much is the energy associated with it. This is the energy associated with motion. That's the energy associated with height h. In this case, now it is with respect to the angle. So how much you pull to the right, you're basically getting a negative sign because you're pretty much subtracting from mgl. That has to be a constant. So what is that constant equal to? Put that to be the extreme end. We are starting from zero velocity. So this term is equal to 0. So that's equal to mgl minus mgl cosine of phi naught. Remember your initial angle, that's your phi naught. Mgl cancels out, and notice every term in this has the mass m in it, and that's the reason why this is independent of the mass. Often when you say there is a gravitational mass and a inertial mass, you try to argue that the mass in this term may be slightly different from the mass in the second term, and that's because these two come from different relation. One is associated, both happen to have been suggested or has been credited to Newton, or Newton was the first one to realize this, and one is the inertial mass that comes in F equal to ma, when we say that mass times acceleration. This is that mass in here. That is also the Newton's law of gravitation, which has g m1 m2 over r squared. That's a separate law altogether, and this mass shows up there. But one argues that is it possible that those two masses are slightly different? In this discussion, we will have all the masses, the inertial mass and the gravitational mass to be the same, and that leads to the cancellation in every term, and that makes this whatever we are discussing, the time period of the pendulum will be independent of the mass, whether it is a 1 kg mass or a 10 kg mass with the same length of the string, the time period comes out to be the same. So that's our equation if you want. This is conservation of energy again, energy associated with motion, energy associated with angle this time. Instead of height, we converted the height into angle, is the same on the left hand and the right. Let me rewrite this equation after the cancellations of the of the angles in there on the same board. I think I can put this in here. There is m cancels out, even one of the lengths cancel out, and mgl, the total, also cancels out. So what we have left is 1 by 2 d phi, so let's say L d phi by dt square minus of g cosine phi is equal to minus g cosine of phi naught. Remember again, this is the initial angle, and that's the angle at any one point in time. This is motion, that's angle. Let me bring the angles on to the right side so that we have motion and angles on two different sides of the equation, and I can write this then as d phi by dt squared is equal to g over L, and that is a factor of 2 times cosine of phi minus of cosine of phi naught. There is a square in here. It's convenient to take the square root. So take the square root on both sides. So that's just to get rid of this quantity here. So that's, and let me do that as 2 squares. Let me go to the next board here. Any questions at this stage? Maybe I should go back. Any questions at this stage at all?
No, not yet. At least not for me, but it might be difficult maybe to follow.
Joanna, Neil, any comments or questions you want to make at this stage?
No, I don't have any questions.
Okay. Okay, so let me proceed. So, so again, rewriting the equation on the right, I have d phi by dt is equal to g over L, and then there's 2 times cosine of phi. So just to have a reference here, so that's your pendulum, and that is phi naught is the initial angle, and phi is the angle at any one point in time, and that's your length L. G is the associated to the gravitational force that Earth is exerting. We would like to solve for, so this is a small change in time, preferably as it can be as small as possible. So you go from one instant in time to the next instant in time. So that's a change in time, but we want to calculate all those tiny changes in time and add them up, and that's what will be the time period. So when phi goes from 0 to 5/2, so you start from, or let me say, you start from phi naught, go all the way to 0, and then all the way to minus phi naught. So let me, how do I write that? So it says 0, and somewhere on here is minus phi naught, right? So it goes down here and then comes back. Right? Phi naught 0, minus phi naught 0, and phi naught. So you go all the way to minus phi naught and come back to phi naught, and that's what will be time period. And it is just by symmetry, or one can, it is not really necessary to do this, but we can say instead of doing that, we can say it is 0 to 5/2 4 times, right? There is no other difference in the, there is no other dependence that is coming up. So it is also will be equal to, if you time period will be go from 0 to 5/2 and multiply it by 4. So let me do that. So I'm going to take the time on the left side and angles on the right side now. So do the algebra. First take this to the right, bring this to the left, and then swap it out. So dt then would be equal to L. So this will get inverted. So that's L over G times d phi over 2 times cosine of phi minus cosine of phi naught. Right, that's your expression for the small amount of change in time. It can be as small as you want, but then you want to add up all those things, so that adding up, we will say, is the idea of integration. So you're going from 0 to phi naught. So this is the idea of calculus we are using. So calculus involves differentiation and integration. Integration especially is interesting in the sense that it is basically adding up. So when you say that is a small change in time, you're basically adding up all those times together, and that's the idea of integration. And the non-triviality in here is that when you're adding up very small amounts of quantities, for example, zeros, so for a very small amount of time, how much distance does it go? Again, it would be 0. If it is really 0, infinitely tiny time, then it should be infinitely tiny distances. But then if you're adding up lots of them, in fact, if you're adding up infinite amount of them, then they can all add up to a unambiguous finite quantity, and that's making that ambiguity go away is basically the idea of calculus and the idea of integration. So we are going to use that. We're going to split this 0 to 5/2 into tiny pieces, then add up all together. And
So
this,
when you are integrating on the time side, would you like to write it time t?
yes, mistake. So I'm going, phi is going from 0 to phi naught, and the time actually is going
T
from
by 4 maybe, right?
0 to total time period, we said is going to be t. So t is the total time period. So this will be t by 4. Right, so
A
1/4.
quarter of that.
Tell that again.
Quarter of that basically.
Yeah, t by quarter of the time period is on the left side, and the right side is the expression for that when you do that for the angles. So this is in terms of the angle. So this is a geometry of the problem, in a sense that the time is related to the distribution of angles. So somehow the geometrical construction of the configuration decides how the time is going to be. And of course, it also depends on the mechanical part, where how much we stretch this. So this is the stretching part, and this is the evolution in time, right? So that kind of decides your time period. And notice this piece is onto the left that is not showing up. Before I proceed from here, let me do a small manipulation that will be helpful when we are talking about the amplitude dependence in this. So what I'm going to do is, let's see, remember that there is this double angle formula for cosine or sine, let's say. So sine of phi by 2 is equal to, or sine square of phi by 2 is 1 minus of cosine of phi over 2. So that's a trigonometric relation. Basically comes from the idea of a right triangle. So the sine of half of an angle, the square of that is related to the cosine. So use this to replace this, and there will be a factor of 1 by 2 in both terms, or 2 times that factor will be there on both terms, so that will go away. So what this turns out to be is t by 4. On the left side is simply that 1/4 of the time period is equal to L over G, and this is 0 to phi naught d phi, and in the denominator this is 2 times. So this is cosine phi. Notice there is a factor of 2 that comes out, or I put this 2 in there. That will go in here. There is already a 2 there, so that becomes F4. So this will become F4. And cosine phi gives you a sine square phi naught phi over 2 with a negative sign. So I'll flip that. So this is sine square phi naught over 2 minus of sine square phi over 2. So that's your expression. Only thing I've done is that instead of writing in terms of angle phi, I have written it, instead of writing it in terms of cosines, I have written it in terms of sine. I still want to work with respect to this amplitude somehow. Remember, this is your phi naught is where my amplitude sits. And for that, I will do one more manipulation. So the first manipulation was to go from cosine to sine. So I want to isolate the amplitude as much as I can. Here, there is a complication that the amplitude is in the integral itself. So that is in this upper limit, which has this non-trivial addition description. So we want to bring that into this expression and keep this constant. So we will do the following substitution. So I'm going to say, let's say this is sine of psi is equal to sine of phi over 2 divided by sine of phi naught over 2. This is basically a scaling idea. What this means is that when phi is equal to phi naught, right? So phi, remember, is an angle that is evolving. So at time t equal to 0, or the initial time when the angle phi is equal to phi naught, the right side is exactly equal to 1. If the right side is equal to 1, sine of an angle is equal to 1, means that psi is equal to pi by 2. So when phi is equal to phi naught, psi is actually equal to pi by 2. So it's kind of you're changing the variables. Instead of talking in terms of an angle that has this physical visual description on the pendulum, we are going all the way from 0 to pi by 2. And when phi is equal to 0, on the other hand, that's much simpler. So when phi is equal to 0, right side is 0. So sine of psi is 0, means psi is equal to 0. So the description of the problem is in terms of the angle phi, where it is going from 0 to phi naught. Instead, now we are saying it is in terms of the angle psi, where it goes from 0 to pi by 2. That has this idea that this will not depend on the phi naught in here. That's the amplitude. Remember, we are interested in that dependent that will get removed from there and put into this expression we just usually call the integrand, right? And we want, but that will of course change the structure in here, and that's what we are going to do in the next couple of steps. I'm going to do that. So let me change the code. Okay, so again, the 1/4 of the time period is equal to L over G square root of that quantity. And now I'm substituting sine psi. Oh, so let me write that down here again so that I think on the board, the left side of the board is not visible to you guys. So this is sine of phi by 2 divided by sine of phi naught over 2. So that's a substitution I'm making, but I want to change the integrals. So it is going from 0 to phi naught earlier. This time it goes from 0 to pi by 2. And I'm interested in what is d psi now. So that's equal to cosine of psi d psi. This is the idea of differentiation, which contributes to this addition that we are talking about. That is, the integration is given in terms of differentials, tiny small quantities. So when you make a small change in psi, how much does sine phi change? It's given by cosine of psi times d psi. And on the right side, this will be cosine of phi over 2 times d phi over 2 divided by sine of phi naught over 2. So I've used the idea of differentiation in calculus. If I make a small change in psi, what's the change in sine psi? That's given by this, and the same thing on the right hand side, that gives you this. That gives the idea that I can change this angle phi that is being used to describe in terms of this new angle, an abstract angle psi. So that's d psi here. So this will be equal to cosine psi d psi. I'm going to put this all to the right. So this is sine of phi naught over 2 divided by cosine of phi over 2. And that is a factor of 2 also in there. So that's a factor of 2. I also have the denominator, earlier denominator in there. So the earlier denominator comes out to be sine of phi naught over 2 multiplied by 1 minus of sine square. Hold on. So that's sine square phi. Yes, so that's sine square psi. There's a lot of cancellations in here. This cancels out, and cosine psi is nothing but 1 minus sine squared psi, so that also cancels out, and it is simply the factor of cosine of phi over 2. That's in there. So that was a small manipulation. Just basically the idea was to, instead of having that amplitude in the on the limit of the integral, bring it out in the integrand itself. So what that leads to is the simple or relatively simpler looking expression for the 1/4 of the time period is equal to L over G times, as a factor of 2 also there, so that's 2, and that's 0 to pi by 2 times d psi over cosine phi by 2 is 1 minus sine square phi by 2, so that's 1 minus sine square phi naught over 2 times sine square psi. So that's a integral, and one would when you study calculus, often you come across integrals and you immediately go through some substitution processes and try to complete the integral. But this is one of the integrals that cannot be done using elementary methods. In fact, there is no solution to this integral. You have to define this as a function itself. So since we cannot do this integral, else we just say that whatever this is, we can evaluate this as good an accuracy as you want. So you define this to be a function itself. So this whole integral is called an elliptic integral. So this is the elliptic integral of the first kind. There is an elliptic integral of the second kind also. In fact, if you have ever thought about what's the perimeter of an ellipse, again, exactly like this integral, it leads to an integral which cannot be completed using elementary functions. So you have to define a special function associated with that, and that's called the elliptic integral of the second kind. So that's a very similar integral. So so given the fact that this integral cannot be done, but remember our goal here was to find out how does this time period depend on this amplitude. Phi naught is sitting in here. Psi is actually really not a variable because you're going to add it up, right? So this is a variable that tells you how to add. Once you add it up, there is no psi. So there is only this amplitude dependence in there. And now let's say that we want to make an approximate. What's the correction? What's the first correction we can make? In principle, I'll go ahead and give you the complete correction later on at the end of the talk. But let's first say, what is the smallest correction you can make? Of course, you can say that phi naught is really small, right? So remember again the diagram here. So you have this pendulum, that's a vertical, and that's your phi naught. Right. So if this amplitude is small, so what do we mean by small down here? So when an angle is small, what we mean is that it is very small. This is usually a notation for very small, significantly small compared to something else. Or whenever we say small, we have to say it is smaller compared to something, and by that we mean 1 radian. And how much is 1 radian? Pi radians is equal to 180 degrees. So that's pi is approximately 3.14 and 180 degrees. So if you divide 180 by 3.14, so that's approximately 60 degrees. So more accurately, this is approximately equal to 57 degrees. So the amplitude, if it is significantly smaller than 57 degrees, then you say this is small angle. But still, why that description? Like, why should we say that this is small? So we want to, so this is what we mean by small, but now we have to associate an error with this. If I make this to be about, let's say, 10 degrees, what is the error I make in the time period? So that's what we would like to know. But let's begin by saying that phi naught is really tiny. It's significantly small, and I can actually set it to 0. So in this limit 0, so that means to say that it is really small and the contributions from the amplitude is really not there, right? So that's an extreme limit, and in that case, this term pretty much goes away, right? Sine of an angle, 0 angle is 0. So this whole thing goes away, and what I get in that case is, so this is now I'm talking about phi naught equal to 0. So then I have a 1/4 of a time period is 2 times L over G. This goes away. The denominator is basically just 1. And I have, this is 0 to pi by 2 times d phi. That's it. This is tiny small angles you add up from 0 to pi by 2, you will get pi by 2 itself, right? So that's equal to, so that's pi by 2, so that's L over G times 2, and I have pi by 2. And it seems like I missed a factor of 2 somewhere. So the time period comes out.
Could you move it to the left side of the board? Can we quickly see where you dropped it?
Oh, where did I drop it? You see. Oh, that's a factor of 2. I see. Okay, so move.
Did you find out?
Why don't I see you, Prachi?
I am also here.
Oh, yeah. Oh, okay. So this is 2. Did I change the board?
Yeah, so I guess this square root of 4, did you take care of it going forward?
Yeah, one sec. I'm not able to change the board. Okay, yeah. So this factor of 4, when I copied it to the right side,
You forgot that, right?
Yeah, I forgot that factor of 2, right?
Yeah.
When I went from this to so this term, and
that will take care of them.
Yeah, so if you notice, there was a factor of 2 here that came from the substitution, but there was an extra factor of 2. So that is, I'll write that down here, right? So that is 1 over square root of 4. Let me write that as square root of 4, so that that's clear that is coming from the earlier description. So that will drop. So there's a square root of 4 there, and that kills this factor of 2. So that's factor of, so 2 cancels pi by 2. So this is exactly equal to 2 pi times L over G. And that's
not equal to 2 pi.
2 pi?
Left hand side,
Oh,
you are
sorry,
still.
yeah, so this goes away, and sorry, pi by 2. And yeah, so that's pi by 2. So if I multiply it by 4, then I get a 2 pi times L over G. So that's the standard expression for the time period. If I multiply this by 4, so it is 2 pi times L over G. And that's what Galileo, I guess it was first time Galileo who realized this dependence on the accurate dependence on this L. Basically, L is proportional to the square of the time period, the quadratic dependence on this time period with respect to length was in a precise manner stated by Galileo, I suppose, but one might want to check on my statement there. Okay, so that's L over, so that's a time period, but now we want to do better, right? I would like to really know what's the error, at least to the first leading order, what's the error you make when you actually have an amplitude. But now, since we have this exact expression, we can actually go ahead and calculate that, at least to a first accuracy. If we know this idea of elliptic integral, we know it exactly, which I will state at the end. But now, for the time being, let's just say that still this angle is small. So it's, instead of saying it is really 0, make it really, it's about 10 degrees or so. We make about 10% error. But within that accuracy, what is the error you make in this time period? So let's go ahead and calculate that. So remember, so again, T by 4 is equal to, we said L over G times 0 to pi by 2 times d psi over 1 minus sine square phi naught over 2 times sine square psi. like this. We're wanting to say that this is small. So if angle phi naught is small compared to 1 radian, so radians usually that's a dimensionless quantity. That also means that sine of phi naught over 2 will be very much small compared to 1. And this whole quantity is also sine is always less than 1. In that case, this is whatever is there under this radical is as a 1 minus a small quantity. So you can expand this out. So you have 1, remember your series expansion. If you have an expression like this, 1 minus x and a square root. So that's nothing but 1 minus x over minus half. So to a good accuracy, if you're if x is really tiny, that's nothing but 1 plus half of x. So that's minus, and a minus sign comes in from there. That's a power in there. There are more terms that will depend on x squared. But if x is small, x squared is going to be further small. Think of it x as 0.01, for example. Then x squared will be 0.0001. So that's about fourth significant digit. So if you can drop that safely if x is significantly small. So that's the idea we're going to use, and we're going to keep this piece. So we're going to expand this out so that t by 4 is, and again, this seems like we are dropping this. Again, it's a fourth significant digit, but I'll come back and give the complete elliptic integral as a plot, and we will understand what's the significance of the other terms. So that's L over G times 0 to pi by 2 times d psi times, now we expand this 1 plus 2 by 2x, so it is 1 plus 1 by 2 times sine square phi naught over 2 times sine square psi. There are higher terms which we are dropping. We are saying we are dropping with the argument that that's going to be significantly small if this is significantly small. That's the idea of small angle approximation. The advantage of doing that is that earlier this integral was not doable. Elliptic integral of first kind cannot be solved using elementary functions. Now the sine square has gone to the numerator, and that's a easy simple integral, elementary integral, and that can be completed. First of all, there is a 1 here. That's straightforward. So that's equal to L over G times the first terms gives you pi by 2. That was your time period in the absence of any, like in the very tiny, the 0 amplitude limit. That's your time period. That's what Galileo gave us. And now this is a correction to that, and that involves an integral of the kind. So that is sine square phi naught over 2 divided by 2, and we have 0 pi by 2 times d psi sine square psi, which is an elementary integral in the sense that in an introductory level calculus, you study this as one of the first applications. So this integral is equal to, so that can be written, remember, using our expression for sine and cosine. I can convert that into cosine, and there will be this first piece that will show up, and this will be equal to pi by 4. Okay. So that's equal to pi by 4. So what we have then is the time period t over 4 is equal to, let me bring this pi by 2 out so that that's my actual time period in the extreme limit of small angle approximation. And then this is a correction to that 1 plus, so I have taken out a pi by 2, so I am left out with 1 over 4 times sine square times 5 over 2. Let me rewrite that on the right side. So that's some of our result here. So the 1/4 of the time period is equal to pi by 2 times L over G times 1 plus sine square pi naught over 2 divided by 4. Notice this is an approximate expression, and we have said that the angle is small. When we did this expansion, we argued that the angle, the amplitude for the angle is small. Then as well, why keep the whole sign itself, expand that out also, and that's good enough. You don't lose any information by doing that approximation. And then this is sine of an angle. Remember, in small angles, sine of an angle theta is approximately itself to theta out itself. Take out, like, it's a good idea to use your calculator and go to radians mode. Don't do the degree mode, go into the radians mode and then type a sine of an angle. And if the angle is relatively small compared to 1, if that in radians, if it is small compared to 1, let's say 0.1, you'll get back 0.1 itself. So it's kind of nice to see that. And in that case, then you have phi naught over 2 squared. So this is nothing but phi naught squared. That's your amplitude in radians divided by 16 then. That's it. So that's your correction. And how much is it? So now we can have an idea of how much mistake you make, what's the error you make when you measure your time period and you really don't obey the small angle approximation, if you want to have the corrections to that. So let's have the simple idea of phi naught, let's say, is equal to 1 radian itself. We said it should be small compared to 1, right? So let's say we say it is 1 radian itself. That's about 60 degrees, right? 60 degrees. So this will be equal to T over 4 will be equal to pi by 2 L over G times 1 plus, this is now 1 radian, so 1 square, 1 over 16 is about 0.06. And notice, as I said, so this is your 1, so that's about 6% error, right? So this is 6% error. So you'll be, instead of measuring a 1, you would actually, if you were to actually have your amplitude contribution, it is 6 in 100. So that's about 6% error. And very soon you would argue that, oh, if I make this phi naught large, it doesn't seem like, because there's an upper limit on this radian, how does that work? But then you have to redo all this calculation. Remember that there was the sine phi in the denominator, and how does this change as a function of that? So for that purpose, you have to bring in the total elliptic integral. So this is pi by 2, so that's your complete. So remember, there is no elementary function that can describe that whole integral. So you give it a special name and a form. So this is K, so it's given by the capital letter K. We use the same K for kinetic energy, so that one cannot avoid repeating it. But in this context, this is the elliptic integral of the first kind. And what is its argument? It is actually sine of phi naught over 2. So if you have a calculator these days on a computer, you can go to pretty much, I think probably you can do it on the browser itself. You write elliptic integral of a sine of a function, and you can do this. But the best idea is to plot this, right? So how will this change? So it will be nice now that we have a complete expression. So that's your amplitude phi naught on the x-axis, and let's say we measure time period on the y-axis. If there was no amplitude dependence at all, it will come out to be a constant. Right, so this is your constant time period that doesn't depend on the amplitude at all, but instead, now we know that there is a correction to that. It is a positive correction for small angles, but what about higher angles? So this is, let's say, so this is your phi, and the maximum it can go, remember your pendulum, remember, so this is your pendulum, and that's where you're stretching, so that's your phi naught. The maximum it can go is pi, right? So that's a maximum you can lift, so that's your pi. Let's say. And it's good to go back and look at the expression there and see what happens at phi naught equal to pi. For small angles, this was nice because this is always less than 1. The second term in the radical is always less than 1, so you're okay. But when this exactly becomes pi, so phi naught is pi, pi over 2 is 1, so this whole thing goes away. And then we have 1 minus sine squared psi. So at the angle pi by 2, that diverges, right? So that goes to 0. The denominator goes to 0 exactly at psi equal to pi by 2 when the amplitude is the extreme scenario where you drop it. So you take the pendulum, think of it as a rigid pendulum, because if it's a string, then it is hard to make it vertical. So think of it as a rigid pendulum so that we can at least in a conceptual sense achieve this. So take it all the way to the top and then leave it and then ask how much time does it take. And it turns out that it is exactly or by exactly, I mean, it goes all the way to infinity. That requires the fact that you plot this elliptic integral of the first kind, and it grows quadratically, but then very quickly it diverges. So as you approach pi here, so that's pi, the time period actually diverges. And this growth, then the question comes, okay, this is a large quantity, but how does this growth, how does this plot look like in the extreme scenario? And it turns out that it is a logarithmic divergence, but we don't have to go into that. That can be seen by the properties of this elliptic integral itself. So for small angles, this grows very quadratically, but very quickly it shoots off to infinity, and that gives us a complete understanding of what's how does the amplitude decide the time period. And that's all, I suppose. Any comments, questions?
So you said like about 60 degrees, you will make an error of 6%.
Correct, exactly. So if you stick yourself to within 60 degrees, you are make it 7%. It's 6.25 if you want, but it doesn't mean anything to go to the next significant digit. So it is 1.06.
Like it is less than 10% error still. If
Exactly, less than 10% all the way to 60
degrees.
degrees, which is not what you would think, right? When you say small angles, we think of 10 degrees, right? So
yeah, but then the point is like after that, if you increase it, the growth will be large.
yes, exactly.
Like the error will be large.
Correct.
Like it is not a linear dependence.
Probably doesn't do justice to what we are talking about. So this is like this actually goes like this. Of course, this depends on the scale that I'm plotting here. So it grows pretty much as quickly goes off. Yeah, correct. So 60 degrees is only 5%, maybe even 70, you might be okay within 10%, but very quickly it blows up.
Okay. And the other thing is like releasing at 180 degree, does it mean to say that it is like, suppose it is a string, we know that it is gonna fall, right? It's just gonna fall
Yes, yes. So,
downwards. So
yes,
it's not going to oscillate at all,
yes. So
right?
we want to make it rigid, right? So
So if
then
you make
comes,
it rigid,
so
then
that's the
this
circle.
infinity is actually representing that it is a stable, unstable equilibrium point, 180 degrees, that it is not going to move from there.
No, that's not it, what it means. What it means is that, let's say you slightly get it off, but the time it takes in the first few angles, that is so small. Either you can think of it right side or to the left side. The time it takes to go all the way till here and then climb the last stage is significant. It is all the way to infinity. So it is really infinity. It is not that it is actually not moving at all, but probably you can interpret it as what you're saying. Yeah, it doesn't move at all from there. Yeah.
To me, an infinity kind of represents a physical impossibility in some,
Um,
in some sense. So I think that that scenario, like the complete oscillation, is not possible in this case.
Again, come to this plot, right? So what we are saying is that there is a growth here, right? So what is the growth is what we are saying. If and what you are exactly talking about is the case when you really take pi. So if you really start from pi, you're right. Unless it will stay there. It's unstable, but it will stay there, I suppose. But we are saying all these expressions are true only for the case when I really drop it off, right? It can be as small as I want. It will be, so that means to say the time period will be very large, as close to infinity as you want, depending on how small the initial angle is with respect to the vertical. That's pi minus the amplitude we are talking about. But we need that initial nudge to describe the problem. Otherwise, it will just stay there.
Mhm.
Does that help
Mhm.
clarify?
Yeah.
Any other comments? Neil, Joanne?
No, I thought it was interesting. Yeah.
Yeah.
So, like there was another thing you said in the beginning that was related with the comment that independence on the mass when
Yes,
two things are dropped was not understood until Newton's time.
yes.
Uh, what, like, you mean to say, like, understood properly in the mathematical terms?
I think until Galileo, I mean, I think
Like
it's not Newton.
Galileo, like there is a, I mean, I'm pretty sure it is anecdotal story, but like, I mean, there is a story about this uh, uh, experiment, right? Could be a thought
Oh,
experiment,
the,
dropping two things from the Leaning Tower of Pisa,
correct.
right?
Yeah,
So,
but isn't it correct that until Galileo, it was everyone thought that?
well, I mean, I think somewhere in the Wikipedia it said that like even before Galileo, two Italian experimenters actually did the experiment. But anyway, like that is going into the details of it. I'm not talking about that. I just wanted to understand the comment you made that it was not understood until the time of Newton.
Yeah, by that, what I meant was that at least the uh, leading description of science, like these days, the leading description is by Newton's law, like we understand physics in this scenario using Newton's laws. Before that, it was, I suppose, Aristotle's theory, where everything was dependent on mass. Like if you drop a heavier object, that was expected to fall faster. So the leading description of science in those days was saying that it depends on the mass. In that sense, I said that
Yeah,
it was not
like
understood
my
at
thing
the
is
time of
that like there are
Newton and
quite
Galileo.
a few things that Newton showed mathematically was already known to Galileo or contemporaries.
Sure,
So
Galileo for sure. I mean, I think it was Galileo who gave this. When I said Newton's time, I think I meant that
okay,
era. Yeah, I
all
didn't
right.
want to take away the credit from Galileo. Of course, Galileo was the first one to say this statement. Yeah, I agree. Is that
Yeah,
what you're
yeah,
pointing out?
okay,
Yeah.
all right. Yeah,
No, I agree. I agree that it
okay.
was Galileo and probably a few others. Yeah. But in a clear form, surely Galileo was the first one to state it in a very, very clear form and authoritatively accepted, like, or others started accepting it was from that point on.
Okay, yeah.
Yeah.
I think I'm good. So I think we can.
Jovan, any questions?
No, sir.
Okay, good. So yeah, feel free to comment or ask anytime. And let me stop here.